What does it mean when a comet seems to be breathing? The three-eyed Atlas, a traveler from another star system, ejects 40 kilograms of water every second into the bottomless cold, too far from the sun to behave this way. Astronomers whisper that it behaves like a living creature. But the story of this comet does not end here. A strange nickel devoid of iron, cyanide in its tail, and mentions of origins billions of years older than our system. Meanwhile, far from this interstellar guest, civilian scientists stumble upon the largest strange radio circles. Mercury and Sirius align curiously in the October sky, raising questions about a possible connection to the three-eyed Atlas, while Blue Origin's flight in October brings more questions than answers. Did he even exist? Stay with me until the end as we confront these troubling questions in our new multi-source format to keep our listeners updated on all the cosmic news happening in our sky. If these mysteries have captivated you as they have me, don't forget to like and subscribe to not miss any updates as it all unfolds in real time. Leave a comment about where you are listening from, what time it is, and whether you believe we are getting the full truth about these world-changing discoveries. And if you want to help our community grow, share this video on social media or just in your group chats. You are the reason we can continue telling such stories, so thank you for supporting us. Part 1. An impossible signal. Imagine, you are floating in the cold silence of space more than 3 times farther from the sun than Earth. Here, sunlight is just a whisper. Ice remains frozen. Comets fall into slumber. Everything sleeps. And suddenly you see it. A comet that literally pours water into the void, ejecting 40 kilograms of this substance into space every second. Not a trickle, but a stream. Water rushes out from a frozen rock, where it is completely out of place. This is the three-eyed Atlas, an interstellar comet that has come to our solar system from another place, carrying the laws from the backyard of another star. The first suspicion came from the Swift satellite, designed to search for gamma bursts. Swift directed his ultraviolet eyes at the three-eyed Atlas at the beginning of the year 2020 and noticed something impossible: a halo of hydroxyl molecules around the comet. Hydroxyl, or OH, is what results when sunlight tears apart water molecules. It is the echo when water dies. When you see OH, you realize that water has just been here, and Swift saw a lot of it. The figures are astonishing. At a distance of 3.51 astronomical units from the sun, the three-eyed Atlas expelled 1.35 times 10 to the 27th power molecules of water every second, which is 40 kilograms per second. In comparison, it's like pouring water equal to the weight of a small car into space every minute. At such a distance, our comets barely make a sound. Our comets of the solar system do not behave this way. Not here. So far from the sun, they are cold, lifeless, practically dead. Ice water needs heat to sublimate, transitioning from solid to gas without melting in between. But there is not enough solar energy at this distance to cause such activity. Our comets awaken only when they approach the sun, starting to eject gas and dust into space. However, Comet 3I Atlas did not receive this signal. You may remember Oumuamua, the first confirmed interstellar visitor. This body was completely dry, without water, without emissions. Just a rolling boulder racing through our neighborhood, silent. Then a second interstellar comet appeared, and it was active but behaved exactly like our comets. It followed a familiar pattern. It was predictable. It was boring, but in the best sense of the word. The Atlas III does not belong to any of these types. It is alive in a way that should not be possible. It ejects water into space, where silence should reign. And the question that troubles every astronomer who pointed a telescope at this body is simple. How? What mechanism could cause this? Is there some exotic ice that we don't know about? Something that sublimates at temperatures we thought were too low? Or are the insides of the comet still warm from its birth billions of years ago? Maybe it rotates in a way that concentrates sunlight on hidden reservoirs of volatile substances? Or is there a chemical reaction happening inside this rock that we have never encountered? Water is just the beginning. The Atlas III also highlights other substances: cyanide, nickel, carbon dioxide in concentrations that make no sense. Each new observation adds another layer to this mystery. Each spectral line appearing in the data raises another question. This is not just a comet that behaves strangely. It is a comet that seems to operate under completely different physical laws, laws written in another star system under different conditions and with different chemistry. And now it is here, in our solar system, giving us the opportunity to observe processes we have never seen before. What keeps astronomers awake at night is this. If the 3A's atlas do what our comets cannot, what does it tell us about its origin? What star system creates such comets? What were the conditions in the protoplanetary disk billions of years ago? And, most provocatively, is this comet simply strange? Or is it a harbinger carrying messages about how diverse the universe can be? Every telescope capable of seeing this body is now directed at it. Spectroscopy, photometry, polarimetry, all our tools. Because the 3 moons of Atlas are not just curiosity, they are a window, a crack in our understanding. And through this crack, we can see something extraordinary. Part 2. Nickel without iron. Comets must follow certain patterns. When they heat up, metal begins to sublimate from their surface. Iron and nickel appear together, like old friends who always travel in pairs. You see one, you see the other. This is one of those cosmic constants we have come to rely on. But the comet Tri-I Atlas did not follow the textbook. A very large telescope in Chile aimed its spectrograph at Tri-I Atlas and discovered something that completely defied expectations. The emission lines of nickel glowed brightly in the spectrum. They were strong, clear, and impossible to ignore, while iron was either absent or present in such negligible amounts that it was almost unrecorded. Nickel without iron. It's like finding smoke without fire. It's like finding traces without legs. This doesn't happen in our solar system. When a comet heats up enough to release metals, iron and nickel appear in predictable ratios because they are bound in the same mineral structures. They form together in similar processes. They sublimate at similar temperatures. They are chemically bonded in such a way that they remain paired. But it seems that Tri-I Atlas was formed somewhere with different rules. At a distance of about 2.8 astronomical units from the Sun, astronomers measured a nickel emission from a comet at 5 grams per second. 5 grams doesn't sound like much until you realize it's happening continuously, second by second, with no iron in sight. This is not a failure. It is a pattern. This comet tells us something fundamental about its composition. Several explanations have been proposed, and none of them are simple. The first possibility is chemical fractionation. Perhaps in the environment where the Tri-I Atlas formed, nickel became part of volatile compounds that easily evaporate, while iron was trapped in refractory minerals requiring much higher temperatures for sublimation. Imagine that nickel embarked on a journey with volatile substances, while iron remained behind in rocky particles. This could create the decomplexation we observe. Another idea concerns organometallic compounds. On Earth, there are molecules like nickel carbon monoxide, where nickel atoms bond with carbon monoxide. These compounds are volatile and evaporate at relatively low temperatures. If 3I Atlas formed in an environment rich in carbon monoxide and other organic compounds, nickel might have been trapped in such molecules. When sunlight hits them, they decompose, releasing atomic nickel into the coma, while iron remains locked in solid particles. Then there is the influence of space weather. Cosmic rays and ultraviolet radiation process interstellar objects for millions or billions of years. Such prolonged bombardment can alter surface chemistry in strange ways. Perhaps radiation processing creates layers rich in nickel, while iron is buried or chemically altered. Perhaps the nickel we observe is merely a shell, a radiation-damaged layer that does not reflect the true composition of the comet. Or perhaps, this is the most thrilling possibility, the Tri-I Atlas formed in a star system with truly different elemental abundances. The stars do not have the same chemical composition. Old stars, stars from different corners of the galaxy, stars formed from gas clouds enriched by various types of supernovae, have slightly different recipes. Perhaps the comet Tri-I Atlas came from a place where nickel was more abundant compared to iron than in our vicinity. Perhaps the parent star had an unusual chemical composition, and this unusualness is now recorded in every molecule of the comet. But one must be cautious. Spectroscopy is a complex task. Detecting weak emission lines against a bright background is not easy. There are detection thresholds. Perhaps iron is present, but lies below the detection threshold. Its radiation may be mixed with other spectral characteristics. We might be observing incorrect wavelengths, and as the comet approaches the sun, heating up, iron will begin to manifest. It would be reassuring. It would mean that the universe still makes sense. But what if it isn't? What if the three-eye atlas reaches perihelion, the closest point to the sun, and iron never appears? What if the ratio of nickel to iron were completely reversed compared to everything we have ever seen? It would be a revolution. This would show that planetary systems can produce comets with metal chemistry so different from ours that our models need a complete overhaul. That's why astronomers are so obsessively monitoring Tri-Eye Atlas. Every observation is a test. Every spectrum is a chance to either confirm our beliefs or destroy them. At this moment, the Tri-Eye Atlas is destroying more than confirming. Part 3. The Comet That Turns On. Comets usually begin to shine brighter as they approach the sun. The physics here is simple. More sunlight, more heating, more sublimation, more gas and dust. This dependence should be smooth, predictable, almost boring. But Tri-Eye Atlas seems to have missed that message. Observers watching the Tri-Eye Atlas noticed something strange about its color. At first, the comet appeared relatively neutral, possibly slightly reddish, which is typical for distant, icy bodies. But as it approaches the sun, it begins to take on a green hue. This was not a subtle change. A bright, eerie green color became evident in the photographs, arising from cyanide molecules and atomic nickel, both intensifying as the comet heated up. It was not smooth. It was superlinear, meaning that the lines of radiation intensified faster than simple geometry could predict. When you are far from the sun, you receive 4 times more sunlight per square meter. This is the law of the inverse square, the foundation of physics. But the emissions of Tri-Eye Atlas grew even faster. Something was unlocked. A new process began to act. Astronomers call it activation. Imagine a temperature threshold. Below this threshold, a certain ice remains solid, locked and inactive. Then the comet crosses this threshold, and suddenly the ice begins to sublimate. Gas production sharply increases. New emission lines appear in the spectrum. It's like a switch in light. At one moment, the process is inactive, and the next it starts. Once it begins, it can develop on its own if there is enough material to fuel it. The comet Tri-Eye Atlas seems to have several such switches. Water began to emerge first, at a distance of 3.5 astronomical units, which is already an anomaly. Then cyanide and nickel appeared, shimmering green as the comet continued to heat up. Each emission line indicates that a different source of volatile substances is involved, as well as that various chemical environments reach the activation threshold. One model that can explain this suggests the presence of large icy particles in the coma. Instead of all activity occurring on the surface of the nucleus, imagine small ice particles being lifted from the nucleus by escaping gas pressure. These particles drift away from the comet, remaining cold and frozen. But as they drift, they are increasingly affected by sunlight. Eventually, each particle reaches its threshold and begins to sublimate, creating a distributed source of gas not only from the core, but also from the cloud of icy particles around it. This may explain the superlinear increase in brightness and the unexpected appearance of new emission lines. Another possibility is thermal fracturing. Comets are dirty snowballs, mixtures of ice and rocks. When one part heats up and expands while another remains cold and contracted, tensions build up. Eventually, something cracks. When ice cracks, it can reveal fresh material that was previously isolated. Suddenly, a new surface for sublimation appears. New volatile substances begin to be released. The comet experiences a surge of activity. 3 and Atlas may be cracking as they heat up, revealing layer after layer of frozen chemistry. Then there are exotic ices. Water sublimates at one temperature. Carbon monoxide ice sublimates at a much lower temperature. Carbon dioxide is somewhere in between. If 3 and Atlas are like an onion with different ices at varying depths or in different areas, then as we heat it, we will see a sequence of activations. First, the supervolatile substances, then the ordinary volatiles, and finally, the most stubborn. Each layer will be peeled away like pages in a book. This is not entirely foreign to us. We have seen comets in our solar system that do strange things. Some comets suddenly activate, increasing their brightness tenfold or more overnight. Some comets break apart as they approach the sun, losing structural integrity due to thermal stress. Some comets remain dormant until their closest approach to perihelion, then explode with activity. But Tri and Atlas do this on a schedule that doesn't match our experience. She is active at distances where she should be inactive. She almost deliberately turns on her switches. and the tension builds. As Tri and Atlas continue their journey inward, will there be more activations? Will we see new emission lines, new molecules we didn't expect to find? Does the activity tire, or will it increase? Each week brings new data and surprises. This is not a predictable comet. It is a drama unfolding before our eyes. Part 4. Where did it come from? Every object in space carries its own story, written in its trajectory. The path he is moving towards reveals where he came from, and the trajectory of the comet Tri-I Atlas tells of events spanning billions of years and thousands of light years. The comet's orbit is hyperbolic, a technical term for an open curve, a path that does not close. 3 comets Atlas came from interstellar space, orbited the Sun, and will leave our solar system never to return. The eccentricity is greater than 1, meaning this comet is not bound to any gravitational field. It is a free agent, a wanderer. She simply walks by. Astronomers traced her path back using old photographs. Precovery is when you search archival data for images of an object before anyone realized its significance. It turned out that Tri-I Atlas had been photographed many times by automated surveys. Some photographs date back to the time when the comet was 6.5 astronomical units away, still approaching, still cold and distant. By combining these observations, the astronomers reconstructed its trajectory with increasing accuracy, and this trajectory points towards a galaxy, but not just anywhere. Modeling orbits combined with data from the Gaia Space Telescope, which mapped the positions and movements of billions of stars, allows astronomers to make informed assumptions about the origin of Tri-I Atlas. The answer is astonishing. The galaxy has structure. The stars are not randomly distributed. Most stars, including our Sun, live in a thin disk, a relatively flat area of young metal-rich stars orbiting around the galactic center. But there is also a thick disk, a population of old stars that move in more inclined and eccentric orbits. These thick disk stars are elongated vertically, spreading above and below the galactic plane, and they are chemically different. These stars are older, formed earlier in the galaxy's history when there were fewer heavy elements, resulting in lower metallicity. The trajectory of Tri-I Atlas suggests it may have originated from a thick disk. If this is true, if this comet formed in this ancient population, then it may be older than our solar system. Our solar system is 4.5 billion years old. Thick disk stars may be older than 7 billion years. This means that the 3I Atlas can carry ice and stones from a time when the Sun did not yet exist. Consider what this means from a chemical perspective. A gas cloud that collapsed to form a thick disk star 7 billion years ago contained fewer heavy elements than the cloud from which our Sun formed. Supernova explosions gradually enrich the galaxy with elements heavier than helium. The earliest generations of stars consisted almost entirely of hydrogen and helium. Later generations of stars, like our Sun, contain a few percent of heavier elements. Stars in the thick disk of the galaxy have intermediate characteristics. They have some heavy elements, but fewer than we do. If the 3I comet formed in such an environment, its composition would reflect a low metal content. It would have less iron, less magnesium, less silicon, all those elements that form planets. However, it would still contain enough volatile substances: carbon, nitrogen, oxygen, locked in ice and molecules. Perhaps this is why we observe such a high ratio of carbon dioxide to water. Perhaps this is why the ratios of metals seem strange. This comet may be a chemical fossil from a time when the galaxy was younger and the periodic table less filled. Of course, we cannot be sure. Tracking an object over billions of years of galactic movement is a challenging task. Gravitational disturbances from passing stars and interactions with the spiral arms of the galaxy complicate tracking, but the fact that the 3Is may be older than our solar system is astonishing. We might be looking at a relic, a survivor, a time capsule from an ancient galaxy. If we can identify its star cluster, a group of stars formed together from a single gas cloud, we will be able to identify its siblings. Other comets, possibly even planets, ejected from the same system are now scattered throughout the galaxy. 3Is may be a single letter in a message written across thousands of light years, and we are just beginning to learn how to read it. What moves along with it? Comets are not just ice and stone. They are cargo ships carrying the molecular inventory of their birthplace. And 3Is carries a very strange cargo. We have already talked about water, 40 kilograms per second. rushing into space to distances where it should not flow at all. This water, or rather the remaining fragments of hydroxyl, when sunlight tears it apart, became the first hint that this comet is unusual. But water is only the beginning of the story. Carbon dioxide is the real sensation. Observations show that Triglass has an extremely high ratio of carbon dioxide to water. In the comets of our solar system, water usually predominates. This is the main volatile component, the key factor of activity. Carbon dioxide is present, but as a secondary player. Three Eyes turns this scenario upside down. Some measurements show that 95% of volatile emissions are carbon dioxide, while water is a less significant component. This is an inverse ratio. It does not resemble what we see at home. Why can a comet be so rich in carbon dioxide? One possible explanation is the formation temperature. Carbon dioxide ice condenses at higher temperatures than water ice. If Three Eyes formed in a warmer region of its protoplanetary disk, closer to its parent star, it could have more actively incorporated carbon dioxide, losing some of its water. Or perhaps the radiation field of the parent star was different, processing ice in a way that our sun does not. Either the giant planets in the system, if they existed, migrated differently, raising dust and mixing materials in unexpected ways. And then there is cyanide. Cyanide, or the CN molecule, is often found in comets. It is the substance that gives many comets their green color. But in the comet, cyanide appeared after water, later in the sequence of heating. In our comets, cyanide and water usually manifest at about the same time, as they have similar sublimation temperatures. The delay in the appearance of cyanide in the Three Eyes comet may indicate that it is in another form, possibly locked in organic molecules that require additional energy to decompose, or frozen in layers beneath water ice. And, of course, there is nickel. Atomic nickel, glowing green, separated from its usual partner, iron. We have already explored this mystery, but it is worth emphasizing again. Every element, every molecule we discover is a clue. Volatile substances tell us about the temperature and pressure during formation. Refractory materials provide information on condensation sequences and thermal processing. The gas-to-dust ratio indicates the structure of the comet and how easily it breaks apart. Now let's talk about the elephant in the room, the hypothesis of panspermia. The idea that life, or at least its building blocks, can spread through space on comets and asteroids. The Three-Eyed Comet contains water, organic substances, and cyanide, which is a key precursor in prebiotic chemistry. If you wanted to create a comet to seed a planet with interesting chemical substances, you would include exactly these ingredients. But let's be completely clear. This is just speculation. There is no evidence that the Three-Eyed Comet carries life. There is no evidence that any comet has ever transported life. The panspermia hypothesis is intriguing. It is plausible in principle, but unproven. She has serious problems. Cosmic radiation is merciless. For millions of years, high-energy particles in interstellar space have been destroying complex molecules. Ultraviolet light from stars does the same. DNA, proteins, even simple amino acids can be obliterated. For life to survive in interstellar travel, it would need to be deep inside a comet, protected by meters of ice and rock. Complex molecules can survive, but not living organisms, rather chemical fossils. Molecules that were synthesized in the parent comet system, possibly in the atmosphere of a planet or on its surface, and then ended up in the comet. These molecules can survive the journey if they are stable enough and well protected. And if we can analyze them, they may tell us what we cannot learn in any other way. They could reveal the atmospheric chemistry of an alien world. They can show us the metabolic pathways from the vanished biosphere. They may be messages written in carbon, nitrogen, and oxygen, waiting for someone to decipher them. This is why some scientists dream of intercepting one of these interstellar visitors, not just observing it from Earth, but sending a spacecraft to match its speed, land on it, drill into it, and collect samples for analysis. The technological challenges are immense. Interstellar objects move quickly at tens of kilometers per second, and to capture one, a spacecraft is needed that is already on the right trajectory or capable of extraordinary acceleration. However, the scientific benefit from this could be colossal. A sample from another star system, chemistry from a different corner of the galaxy, answers to questions we have only just begun to ask. 3. I Atlas is already billions of kilometers away from the inner solar system. We failed to catch it this time, but it shows us what is possible beyond and ignites our interest in new discoveries. Part 6. Citizen Science. Ghost Catchers. Sometimes the most important discoveries happen because someone looks at the data in just the right way, not through algorithms or machine learning, but with a human eye and intuition, and sometimes that someone is not a professional astronomer. Let me tell you about the strange radio circles, ORC. If you haven't heard of them, you are not alone. They were discovered only in 2019, which in astronomical terms makes them practically new. ORCs are huge circular structures visible only in the radio range. You will not be able to see them in optical light or infrared. If you direct a radio telescope at the right section of the sky, you will see them. Perfect rings of radio emissions, sometimes spanning hundreds of thousands of light years, floating in space like cosmic smoke rings. No one knows what they are. The main theory links them to galactic winds or shock waves from supermassive black holes, but frankly, we are still trying to figure it out. They are truly mysterious and the hardest to detect as they are weak and blend with the radio background. Automated detection algorithms typically miss them, as they are trained to find point sources or compact objects, not large diffuse rings. And here the URAD project at home comes to the rescue. This is a citizen science project where volunteers visually explore radio continuum maps, searching for the unusual. They are not looking for anything specific. They seek oddities, and in March 2025, one of the volunteers noted something remarkable. The object was cataloged under the name RAD J13134, 6.9 plus 51320. Sounds a bit dull, but what it represents is much more interesting. A pair of intersecting radio circles, two rings overlapping each other, forming a figure 8. This is the farthest and most powerful ORC ever discovered, found not by an algorithm or a professional survey, but by a person who sacrificed their time to carefully study the data. The discovery was made using low-frequency continuum maps from LOFAR, a network of radio telescopes scattered across Europe. LOFAR generates colossal amounts of data, too large for professional astronomers to analyze manually. Most of the information is processed by automated systems that select potential objects based on brightness, shape, and other parameters. However, these systems have filters and thresholds designed to detect the expected, rather than the unexpected. Here is where the value of human pattern recognition manifests. Our brains excel at identifying what doesn't fit into the overall picture, finding structure in noise, and marking something interesting, even if we can't precisely explain why. The volunteer who discovered RADJ13134 6.9 didn't need to know ORC physics. They just had to look at the image and think, this is strange. And they were right. But it's not just about this one object. RAD at home noted many anomalies. Another volunteer found a gigantic radio galaxy with an unusual ring structure around it. Another discovered a ring at the end of a jet, a feature that theoretical models did not predict. These objects would have been lost in the data stream if not for human observation. The lesson here goes beyond radio astronomy. We are entering the era of data streams. The Vera Rubin Observatory, when operational, will generate 15 terabytes of data every night for 10 years. No human team can review all this information. No set of algorithms can capture every anomaly. We need both machines to process large volumes of data and people to identify strange outliers that don't fit existing patterns. Now let's connect this with the 3i Atlas. Could a civilian scientist have previously detected its anomalies? Could someone, analyzing spectral data, have noticed the signature of nickel without iron before professional astronomers did? Could anyone tracking comet activity wonder, why is this object active so far from the sun? Perhaps, but the main thing is that anomalies like 3i Atlas benefit from as many people observing the data. Professional astronomers have expertise, training, and context, but they also have expectations and models they try to confirm, along with limited time. Amateurs and citizen scientists come with fresh perspectives. They are not constrained by what must happen. They are free to see what is really happening. There are stories of amateur astronomers discovering supernovae, finding asteroids, tracking variable stars. Japanese amateur astronomer Kaoru Akea discovered several comets in the area of the supernova. British enthusiast Andrew Gray became a co-author of the discovery of an unusual stellar outburst. These are not coincidences. They are examples of what happens when passionate people with telescopes or access to data decide to carefully observe the universe. In the future, when telescopes will overwhelm us with petabytes of data, citizen scientists may be the first to respond to cosmic anomalies, possibly marking the next interstellar comet, the next strange radio structure, the next mystery that defies conventional understanding. And when this happens, professional astronomers continue their research, delving into physics. It is a partnership, and like all good partnerships, it is stronger than each element alone. Civil science against professional control. But let's not pretend that this is complete cooperation and joy. There is tension here, real tension. Because the opening of doors for citizen science is linked to the need to deal with false positives, well-meaning enthusiasts marking objects that turn out to be artifacts or noise, conspiracy theorists seeing alien signals in every data glitch, and professional astronomers understandably worrying about this. The Royal Astronomical Society and other professional organizations discuss this in detail. On one hand, citizen science reduces the burden. It allows projects to process more data than would otherwise be possible. She engages the public and creates interest in science. On the other hand, quality control is crucial. A discovery is not considered a discovery until it has been verified, re-verified, and peer-reviewed, which takes time and expertise. False positive results are a real problem. Someone marks an object as unusual. Astronomers spend days or weeks investigating, only to find it's just instrumental noise, a satellite trace, or a cosmic ray hit. This is time that could have been spent on real discoveries, and as the number of false positives accumulates, astronomers begin to view reports from amateur researchers skeptically. The signal-to-noise ratio decreases, fatigue sets in, then confirmation bias appears. When people search for something specific, they tend to find it, even if it isn't there. This happens with professionals too, but training and review provide control. Enthusiasts of such checks may not exist. They might see a pattern in random data and convince themselves that it is true. This is how claims about alien megastructures around Tabby's star or messages in pulsar residuals emerge. Calibration and errors are another problem. Professional astronomers know how to assess measurement uncertainty. They understand when a signal is statistically significant and when it is just noise. Amateurs may not know this. They can report detections that are actually just fluctuations of 1 sigma, insignificant in the scale of statistical analysis. And there is a problem with the volume of data. If a citizen science project becomes too popular and too many people start marking too many objects, the professional astronomers responsible for further research may become overwhelmed. They cannot investigate everything. They need to set priorities, which means that some real discoveries may be missed simply because they are lost in the flow of data. But here's the thing. These problems are not insurmountable. They are challenges, not reasons for refusal. Learning protocols can help. If civilian researchers and scientists are trained to assess data quality, recognize artifacts, and evaluate uncertainty, the rate of false positives will decrease. Mentorship programs where experienced enthusiasts guide newcomers can uphold standards. A validation system where multiple independent volunteers must mark the same object before it undergoes professional verification can filter out false discoveries, and the possibilities here are immense. Crowdsourcing anomaly searches allows for more thorough exploration of large data sets. Cross-checking by multiple independent observers reduces the likelihood of a real anomaly being missed because one person is simply not up to the task. The diversity of perspectives means that people from different fields can notice patterns that specialists overlook. Let's return to the object called the Three-Eye Atlas. Could a civilian astronomer have noted its nickel anomaly early on? Spectral data is available to everyone. Anyone with the right software can download and analyze them. But spectroscopy is a complex task. It requires understanding line identification, wavelength calibrations, and signal-to-noise ratio assessment. It's not something you can just do casually. But perhaps with training, support, and a community of like-minded individuals, someone could have noticed the oddity before it made the headlines. The same goes for the speed of water production. Brightness measurements over time, which have comet-like curves, are often provided by amateur astronomers. If these enthusiasts had analyzed ultraviolet data from the SWIFT mission and were trained to recognize unusual activity, they might have noted the superlinear increase in brightness of Tri-Eye Atlas. They could have said, "This doesn't look like an ordinary comet," before professional research confirmed it. Past experiences of discoveries made by citizens proved that it works. The transit method of exoplanets, where planets are detected by small dips in a star's brightness as the planet passes in front of it, was advanced by citizen scientists analyzing Kepler data. Projects like Planet Hunters have discovered many confirmed exoplanets. Asteroid hunting enthusiasts found objects near Earth that were overlooked by professional research. Amateur hunters of new stellar flares regularly outpace professionals in discovering such events because they observe every night with small telescopes, while professional observatories operate on a schedule months in advance. The conclusion is not that we should replace professional astronomers with amateurs. That is absurd. The conclusion is that we need both. We need professionals for deep expertise, theoretical foundations, and strict validation, and we need citizen scientists for broad coverage, fresh perspectives, and a vast number of observers. This is not a competition, but a partnership, and in the age of data flow, this partnership is essential. Part 8. The Effect of Coincidence. October 2025 brought something unusual: excellent conditions for observing both Mercury and Ceres. Mercury, the closest planet to the Sun, appeared for favorable evening observation, shining brightly high above the horizon after sunset. Ceres, the largest object in the asteroid belt, reached opposition, meaning it was directly opposite the Sun in the sky, at its brightest and closest position to Earth. On social media, people began to connect the events. Mercury is visible, Ceres is visible, and this strange interstellar comet, the Three Eyes of Atlas, behaves as if it is alive. Are they connected in some way? Is there some cosmic coincidence happening? Perhaps the gravitational fields of the solar system somehow activate or enhance the activity of the comet. Let's clarify. No, there is no connection. Mercury's orbit has nothing to do with the outbursts of the interstellar comet. The position of Ceres relative to Earth does not affect the chemical processes occurring billions of kilometers away. These are independent events that coincided in time, and nothing more. However, people like patterns. We are wired to seek them, a trait that aids survival. Our ancestors, who noticed that certain berries caused illness and the tracks of some animals led to prey, had a better chance of survival than those who did not recognize patterns. Therefore, our brains are hypersensitive to patterns, sometimes to the extent of finding them where they do not exist. This is pareidolia on a cosmic scale. Pareidolia is when we see faces in clouds, hear voices in static. It is a glitch in pattern perception, and it happens with celestial events constantly. Ancient cultures saw signs in planetary alignments. When a comet appeared during battle, it meant the gods were angry. When the planets gathered in one part of the sky, it foretold the birth or death of kings. The year 1910 serves as an excellent historical example. This year, Halley's Comet returned, passing through the inner solar system on its 76-year journey, and people were horrified. Astronomers discovered cyanogen, a toxic gas in the comet's tail. Newspapers printed sensational headlines. The poisonous tail of the comet will sweep over the Earth. People were buying gas masks, some sealed their windows. There were even reports of suicides by those convinced that the comet would kill them. Of course, nothing happened. The comet's tail is incredibly sparse, practically a vacuum by earthly standards. The amount of cyanogen that actually reached Earth was negligible, undetectable. The comet posed no threat, but the coincidence of its appearance with other unrelated events, solar activity, political unrest, earthquakes, only fueled the panic. People connected unrelated events. We are witnessing the same with the Three Eyes of Atlas. The comet is strange, truly anomalous. Mercury and Ceres were visible at the same time, and suddenly people begin to build theories. Perhaps the comet is awakening under the influence of some resonance of the solar system. Its trajectory might be slightly altered by gravitational disturbances. This could be part of a larger pattern that we do not yet understand. Astronomers have conducted calculations. The gravitational influence of Mercury on an object in the outer solar system is practically zero. Mercury is small, only slightly larger than our moon, and it is far away. Ceres is even smaller and even less influential. The combined gravitational influence of all the planets in the solar system cannot significantly affect the behavior of the Triglass Atlas comet at the distances we observe it. The comet behaves as it should due to internal processes, solar radiation, and its composition, not because of Mercury's position in its orbit. However, facts do not always matter when there are appealing narratives. The human brain craves stories. We want events to be connected because disconnected events seem random, chaotic, and meaningless. If a comet's activity is linked to the position of planets, order emerges, predictability, and meaning arise. If they are not connected, then we live in a world where strange things happen for no reason, and this is psychologically uncomfortable. The confirmation effect amplifies this perception. Once you start looking for connections, you find them everywhere. Mercury was also visible during the previous comet discovery. Sirius was near opposition when another unusual object was discovered. It doesn't matter that Mercury is visible several times a year, while Sirius reaches opposition every year. It doesn't matter that unusual astronomical discoveries happen constantly. The brain filters out discrepancies and only remembers instances that fit the narrative. Social media amplifies this effect exponentially. In the past, if you had a theory about the influence of planetary alignments on comets, you could share it with friends who would likely dismiss it, and that would be the end of it. Now you publish your theory online and instantly find a community of like-minded people. You share links, images, and graphs showing alignments. Someone adds new evidence. Another person shares it further. Soon, you have a full alternative narrative competing with the scientific explanation. The lesson here is not that people are foolish or gullible. The lesson is that coincidences are very powerful, and our brains are not always set to ignore them. Statistically, with thousands of astronomical events happening constantly, some will coincide purely by chance, and these coincidences will seem significant, even if they are not. This is important because it affects how people interpret anomalies like the three-eyed atlas. If you are inclined to see cosmic conspiracies, if you believe that alignments matter, then the strange behavior of the comet becomes evidence of something greater. Perhaps this is not a natural comet at all, but an artificial one, possibly responding to planetary signals. Maybe it's part of some grand cosmic mechanism that we do not understand, leading us to an even stranger chapter of this story. Mechanisms of deception, conspiracy theories, and how people turn scientific mysteries into cultural myths. Part 9, Update for October 2025. Did this really happen? October 8, 2025, Blue Origin mission number 36. 6 passengers, 11 minutes, 1 mysterious passenger whose name remained a secret until landing. The capsule was launched, crossed the Kármán line, floated in microgravity, descended on parachutes, and landed in the Texas desert. Success. Another flawless flight for the company's space tourism program, their 15th rough mission. Quite ordinary. This is the official version. This was reported in the news. Some journalists mentioned it on social media. The mysterious passenger was revealed after landing, a private individual who requested anonymity during the flight but gladly agreed to mention afterward. Nothing unusual. People often pay for privacy. But here is what is strange. Here is what continues to torment those who closely watch space flights. Silence. A terrifying, almost suffocating absence of light. No viral videos, no trendy hashtags, no celebrity reactions, memes, or social media breakdowns. Spaceflight. A commercial crew crosses the boundary of space. What would have been the main news just a few years ago barely received noticeable attention. Think about it for a moment. 6 people left the planet. They experienced weightlessness, saw the curvature of Earth against the black cosmos, and returned safely. It's unusual. This should be unusual. But the internet just shrugged. Social networks switched to something else in a few hours. The story vanished like smoke. Why? Why so little illumination? Usually Blue Origin publishes footage from the cabin, beautiful shots of passengers floating, laughing, pressing their faces against the windows. Where are these images? Why haven't they appeared on all news sites? Why did the mysterious passenger not spark curiosity? Who are they? Why did they want anonymity? These are natural questions that usually generate days of speculation and interest. Instead, there is silence. Radio silence. As if the flight occurred in a vacuum, not only cosmic but also social. And this vacuum, this absence, begins to feel significant. Silence becomes louder than any announcement. You start to ponder. You begin to ask uncomfortable questions. Did this flight really happen as described? Were there 6 passengers, or was the manifest different? Was the mysterious passenger real, or a fictional character to explain the absence of pre-flight? Did the capsule really launch on October 8th, or were the footage reworked from a previous flight with a new date? These are paranoid thoughts, conspiracy theories, a way of thinking that sees shadows everywhere and trusts nothing. But sometimes the absence of evidence seems significant. When something should sound and does not, one must ask why. Let's compare this to April 2025, just 6 months before. Blue Origin launched another New Shepard mission, and it exploded in public consciousness, not due to a malfunction, but because of who was on board. Katy Perry, Gayle King, the first all-female crew, high-profile passengers with millions of followers. This was the flight meant to attract attention. And it did attract attention, but not the kind Blue Origin expected. Just a few hours after the broadcast ended, conspiracy theories ignited. People began to claim that the flight was fabricated, dissecting every second of the video for discrepancies. The behavior of hair in zero gravity became a battleground for analysis. They were questioning whether they were handling things correctly, if they were moving too unnaturally, whether it was real hair or a wig or computer graphics. The capsule door became another point of discussion. Someone noted that it opened differently than on previous flights. People posted photos for comparison, drew arrows, circled supposedly anomalous details. Wasn't the latch on the other side last time? Didn't the door used to open outward? Why does it look different? Then truly strange theories emerged. Claims about green screens. Accusations that passengers were filmed in a studio with fake windows displaying pre-recorded footage of Earth. Accusations that the hands looked like mannequins, too smooth, too plastic. Complaints about the lack of visible burn marks on the capsule after re-entry into the atmosphere. Every detail became evidence of deception. Journalists methodically refuted these claims. Hair behaves strangely in microgravity because there is no gravity pulling it down, so it reacts to air, currents, static electricity, and random movements. The hatch opening mechanism is the same across all flights. Different angles and lighting create the illusion of differences. Reflections in the visors distort perspective. Burn marks are not always noticeable depending on the cleanliness of the landing site and camera resolution. However, refutations did not stop the theories. On the contrary, they only fueled their beliefs. People wanting to believe in the fabricated flight perceived the denial as a cover-up. They delved deeper into research, finding more evidence, constructing complex models of how the deception was carried out. The conspiracy became self-sustaining. Now we have 2 flights, 2 missions, 1 rocket, the same basic profile, a 6-month difference. One attracted a storm of attention and doubts. The other barely made a sound, raising the question of which is more suspicious. Part 10. Cosmic Mysteries as Reflections. The universe continues to throw unexpected surprises at us. Objects that do not fit our perceptions, signals that make no sense, phenomena that disrupt our carefully constructed models. And each time, without exception, we do 2 things. First, we rush to understand it scientifically. Secondly, we project ourselves onto this mystery. Remember Oumuamua, 1917. The first confirmed interstellar object passing through our solar system, elongated, reddish, and accelerating, not significantly, but noticeably, as it left the solar system. This acceleration did not fit a purely gravitational trajectory. Something was pushing it. Scientists speculated that it could have been a gas outburst. Although no gas was detected, perhaps Oumuamua was releasing small amounts of volatile substances, thereby creating thrust like a weak comet. Or perhaps it was a hydrogen iceberg, frozen H2, sublimating silently. Or maybe it was a fragment of a shattered planet, its shape and rotation creating effects of radiation pressure. But a group of people, including some scientists, proposed another hypothesis. What if Oumuamua was artificial? A light sail, a solar sail, a thin layer of material pushed by sunlight. This could explain the acceleration, and if it was artificial, perhaps it was a probe from another civilization. Perhaps he explored space, or maybe he was abandoned, a piece of space debris from a long-gone alien society. The same happened with Tabby's star, KIC 8462850. A star in the Kepler field displaying strange eclipse patterns, deep, irregular dips in brightness sometimes reaching 20% or more. No planet could dim the light so much. No planet is large enough to block that much light. The gaps did not occur regularly, as would be the case with a planet's transit. Astronomers proposed explanations in the form of dust clouds, cometary swarms, and debris from planetary collisions. But one paper, half in jest, suggested the idea of an alien megastructure. A cube and a swarm, millions of solar panels or living modules rotating around a star and collecting its energy. This could block light regularly as the structures moved. It somewhat matched the data. Strange radio circles, fast radio bursts, a 3-axis atlas. Every riddle becomes a screen onto which we project our hopes and fears. Are we alone? Is the universe indifferent, or does it have intentions? Are there others like us, or are they so alien that we cannot understand them? Psychology is strong here. Pareidolia, the ability to see patterns in randomness, is part of this. We see faces in clouds, hear voices in white noise, and recognize intelligence in astronomical anomalies. This is not foolishness. It is how our brain works. We are machines for recognizing patterns, and we tend to have false positives. It is better to mistake a shadow for a predator than to mistake a predator for a shadow. There is also an existential thirst. We want contact. We want to know that we are not the only sparks of consciousness in the vast, cold universe. Each anomaly carries a chance, a possibility, a door that can open the way to something extraordinary. And we persistently knock on these doors. The three-axis atlas is a mirror. In his glowing green haze, we see the reflection of our own curiosity, thirst for meaning, hope that the universe is stranger and more wonderful than we can imagine. Perhaps it is so. Perhaps one day we will find something truly inexplicable that will force us to rewrite physics or accept that we are not alone. But that day has not yet come. For now, we have a comet. A strange comet. An intriguing comet, but probably just a comet. And that's enough, because even natural mysteries are something unusual. Part 11. Archive of Alien Systems. Imagine the galaxy as a library, not a library of books, but a library of objects. Comets, asteroids, wandering planets, ejected during the chaotic formation of planetary systems and cast into interstellar space. Each object is a message in a bottle, carrying information about the star system in which it was formed. And sometimes one of these bottles ends up on our shore. Such are the interstellar objects. They are postcards from alien systems, not in the sense of extraterrestrial intelligence, but in the sense of foreign, different, formed under conditions unlike those in our solar system. Each discovered object is a data point, a single specimen, and with enough specimens we begin to understand the diversity of the chemical composition of planetary systems. The comets of our solar system are relatively homogeneous. They formed in the same protoplanetary disk from equally mixed gas and dust under the influence of the same stellar radiation. Of course, they vary. Some contain more carbon monoxide, others more water, depending on where in the disk they formed and what temperatures they experienced. But they are family. They are brothers and sisters, at least cousins. Interstellar comets are strangers. They formed in other places, under different stars, in disks with different compositions, temperatures, and dynamic conditions. So far, all we have seen were different. Oumuamua, a dry, non-gassing, oddly shaped object, accelerating in a mysterious way. It did not resemble our comets. She did not behave like our comets. If she was a comet, it was of a type we had never encountered. Boris, rich in carbon monoxide, exhibited typical comet behavior, but with a gas-to-dust ratio indicating colder formation conditions than most of our comets. She looked familiar, but with barely noticeable differences, like a dialect of a language you know. Atlas, water and carbon dioxide erupting from great distances, nickel without iron, cyanide appearing late. Nothing in her behavior fits our experience. She speaks in a language we barely understand. Three objects, three wildly different chemistries. If we extrapolate and assume these three represent a broader population, the diversity of comet compositions in the galaxy is astonishing. Not all planetary systems produce comets like ours. In fact, most likely, most do not. Consider what this means. In some systems, comets may be dominated by nitrogen ice, like the surface of Pluto. In others, methane may be the main volatile substance. In systems with more massive stars, the snowline, the distance at which water ice can condense, is farther out, allowing comets to form in colder regions and carry various mixtures of volatile substances. In systems with migrating giant planets, the disk stirs, mixing materials from various temperature zones, creating comets with unusual, hybrid compositions. Could some comets carry molecules we have never seen? Molecules that are thermodynamically possible but require pathways for formation that do not exist in our solar system, exotic organics, strange isomers, compounds that will make a chemist's eyes light up. The universe is likely vast, and the parameter space for stellar masses, disk compositions, radiation fields, and dynamic environments is colossal. Nature carefully explores this space, and some of its results can be strange. Let's take a step further. If life requires certain chemical building blocks, water, organic compounds, phosphorus, nitrogen, sulfur, then comets lacking these ingredients are sterile. They cannot initiate life, nor can they deliver pre-organic chemistry to planets. Perhaps many interstellar comets are lifeless. Perhaps Oumuamua was a dead rock spinning in emptiness, but if even a small part of comets carries the necessary chemistry, it is important. Since comets are galactic wanderers, they travel between stars, crossing light years, and if they contain organic molecules, amino acids, or perhaps even dormant microbes hidden deep inside, the building blocks of life could spread throughout the galaxy. This is panspermia, the hypothesis that life can be transferred between worlds on comets or asteroids. It is controversial, unproven, but not impossible, and three objects like Oumuamua with water, organic matter, and cyanide have the necessary ingredients. This is probably not life, but chemistry that could lead to life if delivered to the right planet. Every interstellar object we discover expands our sample. At the moment, we have 3 such objects. In 10 years, there may be dozens of them. In 50, hundreds, and with each one we will measure composition, trajectory, activity patterns, creating a statistical understanding of what exists there. Perhaps we will discover that water-rich comets are common, produced by most planetary systems, or maybe we will find that our solar system is an exception, with water-rich comets being rare and most systems creating dry carbonaceous bodies. Both answers are fascinating, and perhaps we will find a comet with clear biomarker molecules that are hard to explain without biology, phospholipids, complex organic compounds with chirality, and isotopic ratios indicating metabolism. This would be revolutionary. This would confirm that life originated elsewhere, that biochemistry is not unique to Earth. We have not found this yet. As we can judge, Oumuamua does not carry life, but it carries information, and information is the currency of science. Every interstellar guest is a gift, a free sample delivered to our door. All we need to do is look closely. Part 12. Nickel is the messenger. Let's return to this nickel anomaly. This is not just curiosity, it is a hint. A chemical fingerprint reveals where someone has been. The stars are factories. Nuclear fusion in their cores takes hydrogen and helium and creates heavier elements: carbon, nitrogen, oxygen, silicon, sulfur, iron. When massive stars explode as supernovae, the explosion creates even heavier elements, including nickel. These elements scatter into space, mix in gas clouds, and eventually become part of new stars and planets. But not all stars have the same composition. The content of heavy elements, what astronomers call metallicity, varies. Young stars, formed recently from gas enriched by generations of supernovae, have high metallicity. Old stars, formed in the early epoch of the galaxy when supernovae were fewer, have low metallicity. Nickel and iron are produced in supernovae, but in slightly different proportions depending on the type of explosion. A type Ia supernova, where a white dwarf absorbs matter and explodes, generating different ratios of nickel and iron than core collapse supernova, where a massive star implodes. If the comet Tri-Atlas formed in a system whose gas cloud was enriched with an unusual combination of supernova types, its nickel and iron ratio may be distorted. Currently, we assume that the Atlas trio may originate from a thick disk of older stellar population. Stars in the thick disk have lower overall metallicity, but the ratios of various heavy elements can vary. If the nickel discrepancy we observe in the Atlas III reflects the composition of its parent star, then this comet serves as an indicator. It tells us about the chemical evolution of the galaxy in ways that are not easy to investigate. The thing is, we can analyze the atmospheres of stars spectroscopically. We can measure their iron, nickel, and everything else, but the stars are far away. We can only study a tiny fraction of them in detail and cannot explore stars that no longer exist, stars that lived and died billions of years ago. But comets from those systems, their time capsules, preserve the chemical conditions of their birth. If we could directly explore the Atlas III, analyze its isotopes, trace elements, and mineral structure, we would hold a piece of a star system that could be billions of years old and located thousands of light years away from us. We would read a story written by atoms. Now let's consider a speculative idea on the edge of fantasy, but discussed in certain circles. Could metal anomalies, such as high nickel, be signs of processed material? Not naturally processed, like thermal metamorphosis, but technologically processed. If an advanced civilization were engaged in asteroid mining, metal processing, and constructing structures in space, they would generate waste, slag, tails, emissions. This material would have unusual elemental ratios due to industrial processes. You extract iron for construction, possibly discarding nickel residue, or using nickel for a specific purpose and discarding everything else. If a comet formed in a debris disk containing industrial waste, it could include these anomalous metals. And then, after millions or billions of years, this comet is ejected, wandering through the galaxy and entering our solar system. We detect a nickel anomaly and begin to ponder. To be absolutely clear, there is no evidence that the Atlas trios are artificial or contaminated with techno traces. None. This idea is so speculative that it borders on science fiction. Most scientists dismiss it without hesitation, but it is not physically impossible. In the absence of a clear natural explanation for the splitting of nickel ions, even the wildest ideas can be heard. A more likely explanation is related to precursor chemistry, nickel in organometallic compounds, and fractionation during condensation. There is some process that we are not yet aware of, occurring under conditions common in other star systems but rare or absent in ours. But here is what truly inspires me. Each comet carries a chemical signature, a barcode written in elements and isotopes. If we create a library of these signatures, if we catalog the compositions of dozens or hundreds of interstellar objects, we can begin to map the galaxy. We could compare the chemical signatures with the trajectory. A comet coming from the direction of the galactic center may have different content than a comet from the outer shell. A comet from the dense disk may show age signatures. We could use comets as traces of galactic structure and evolution. Imagine a future where interstellar objects are so common, where our detection technologies are so advanced that we catalog dozens of them each year. Each comet undergoes spectroscopic analysis. Each trajectory is tracked as far as possible. The composition of each object is added to a database. Ultimately, patterns emerge. We will discover that comets from one region of the galaxy are systematically rich in carbon. Comets from another region are rich in water, and we are beginning to understand why. Perhaps carbon-rich regions formed more low-mass stars, which have different chemistry in their planetary disks. Perhaps water-rich regions had more supernova activity, enriching gas with oxygen. The object 3 eyes is the beginning of this library. One element, one data point, but this is just the start. And the nickel, a strange split nickel, reminds us that each data point has its own story. Each relationship of elements is a clue, and if we are patient and careful, we can read these stories and piece together the story of the galaxy. Part 13. The invisible population. 3 objects. Oumuamua. 2 objects in the distance. 3 eyes. 3 confirmed interstellar visitors in 7 years. It's few, but enough for statistics. Enough to assess how many more objects are out there, passing unnoticed. Astronomers conducted calculations based on detection frequency, observation coverage, and the observed properties of these 3 objects. They estimate that at any given moment, there are likely several interstellar objects within Jupiter's orbit. Small, dark, moving quickly, invisible to most telescopes. We discovered 3 objects because we were lucky. They passed close to Earth, were bright enough, or were in the right part of the sky when the correct telescope was observing. How many are we missing? Hundreds? Thousands? For every interstellar comet we discover, dozens likely pass unnoticed. Some are too dim, some move too quickly to track, and some appear in parts of the sky we do not monitor. Detecting objects in interstellar space is a challenging task, but it is becoming increasingly accessible. New observatories with unprecedented sensitivity and sky coverage are starting their operations. The Vera Rubin Observatory, currently under construction in Chile, will scan the entire visible sky every few nights, capturing even the faintest objects. It will be able to detect asteroids, comets, supernovae, anything that moves or changes, as well as find interstellar objects. The Rubin Observatory is expected to register 1 interstellar object per month, possibly more, meaning at least 12 such objects a year and over 100 confirmed interstellar visitors in 10 years. This is already a statistical sample sufficient to begin making serious conclusions about the composition, origin, and populations of these objects. The Square Kilometre Array Radio Telescope Network, being developed in Australia and South Africa, will also contribute. Radio observations can detect molecular emissions from comets, even very faint ones. This network will be able to spot interstellar comets that remain unnoticed by optical telescopes. Space ultraviolet and infrared telescopes will catch comets that are active but hidden in the optical range. Each new tool expands our ability to detect these faint, fast-moving objects. However, detecting is one thing, and studying is quite another. Interstellar objects move quickly at speeds of tens of kilometers per second relative to the Sun. Therefore, by the time we notice them, analyze their orbits, and plan further observations, they may have already left our solar system. Oumuamua was already leaving our system when we opened it. We managed to take only one good shot, and then it disappeared into the distance, becoming too faint for observations. We were able to catch 2I Borisov on approach, which gave us months for its study. Telescopes around the world focused their gaze on it. We received spectra, light curves, and detailed observations. This is the perfect scenario. We also noticed 3I Atlas relatively early. We are gathering good data, but soon it will reach perihelion, past the Sun, and disappear back into darkness. And then he will disappear forever if we do not intercept him. There are proposals for creating missions to intercept interstellar objects. These are spacecraft designed for rapid launch, capable of accelerating to meet an interstellar visitor while still within the inner solar system. The technical challenges here are immense. It is necessary to have a spacecraft on standby, ready for launch at short notice. A powerful engine is needed to match the speed of the object, along with tools capable of analyzing composition, structure, and possibly even collecting samples. However, the reward for these efforts will be extraordinary. Imagine we land on an interstellar comet, drill its surface, collect ice and stones from another star system, and bring them back to Earth for analysis in laboratories. The scientific discoveries we could make with this material are almost beyond imagination. We could determine the exact isotopic ratios that reveal the nuclear processes in the parent star. We could analyze complex organic molecules in ways that cannot be done remotely. We can study amino acids for prebiotic chemistry, and perhaps even find fossilized microbes if we're lucky. Even if life is not found, we will learn much about the chemistry of extraterrestrial planetary systems in astonishing detail. Each molecule, each mineral, each isotope will be a clue. Some scientists are already planning such missions. Concepts exist, budgets are proposed. This is not science fiction, it's engineering, real engineering, but feasible. In 50, maybe 100 years, we might catalog hundreds of interstellar objects. We can intercept a dozen of them. We can return samples from half a dozen objects. And with this data, we will gain a comprehensive understanding of galactic comet populations, the diversity of planetary systems, and perhaps even the prevalence of the building blocks of life in the galaxy. Triapolis is a premonition, a glimpse of what is possible. He shows us that interstellar comets are not just rare curiosities. They are widespread, they are everywhere, and they carry information that we desperately want to obtain. An invisible population exists, spinning in the darkness, waiting for us to find them, and we will find them. We will catalog them, study and piece together the puzzle of how planetary systems form, how chemistry varies across the galaxy, and perhaps how life is actually distributed. Part 14. When the anomaly accumulates. Time: 0.5 seconds. Let's step back and look at the bigger picture. Because Triapolis is not the only strange phenomenon in astronomy at the moment. Far from it. Strange radio circles, mysterious rings of radio waves, the origin of which is unknown. Fast radio bursts, impulses of radio energy lasting milliseconds from distant galaxies, the mechanism of which is under discussion. Tabby's star, strange patterns of brightness variation that remain unexplained. Oumuamua, an interstellar object with anomalous acceleration, Tri-Atlas, a comet with impossible water production and metallic anomalies. And these are just the most well-known cases. There are many, possibly hundreds, of lesser-known anomalies. Temporal events that do not fit known categories, spectral characteristics that should not exist, objects moving in ways that are hard to explain. Astronomy confronts the incomprehensible, and this is new. For most of the 20th century, astronomy suffered from a lack of data. You pointed the telescope at something, took a photograph for the spectrum, and analyzed the results for months. Discoveries were rare, and anomalies even rarer. When something strange appeared, it was carefully analyzed, as there weren't many other objects to attract attention. Now, however, we are drowning in data. Automated reviews generate terabytes of information every night. Heavenly surveys catalog billions of objects. Gravitational wave sensors detect mergers. Radio telescopes constantly scan the sky. We register more objects than we can explore, and with the increase in data volume, a high frequency of anomalies emerges. If you look at 1 billion objects, even if only 1 in 1 million is strange, that will be 1,000 anomalies. Most will be the result of instrumental artifacts, data errors, or misclassifications, but some will be real, and analyzing them will take time. We are in an era where anomalies outpace theory. We discover things faster than we can explain them, and this is both exciting and dangerous. Exciting because new phenomena lead to new physical discoveries. The discovery of pulsars, gamma bursts, and gravitational waves began with unexplained observations. Anomalies are where breakthroughs occur, but it's dangerous because hype cycles can spiral out of control. Each anomaly is presented as potentially revolutionary. Giant alien structures, signs of engines, wormholes, interactions with dark matter. This excites the media and the public. But then, in 9 out of 10 cases, the anomaly is explained by something trivial. Clouds of dust, instrumental noise, misidentified known objects. The danger lies in losing trust. People hear about potential aliens repeatedly, but it's just dust, and they stop trusting scientists, thinking science is just wild speculation. Or worse, they stubbornly insist on an alien version, deciding that scientists are hiding something. Tabby's star is a warning. When the hypothesis of a giant alien structure hit the headlines, the public became interested. Social networks exploded, news articles actively discussed it, and when subsequent observations showed that the eclipse depended on wavelength, indicating dust rather than solid structures, reactions began. Some accepted the explanation, while others insisted that scientists were wrong or lying. But here's the thing. Tabby's star is still intriguing. The dust explanation does not fully account for all observations. Long-term monitoring shows complex variability. This is a strange star, possibly surrounded by a disk of debris from a planetary collision, perhaps doing something we do not fully understand yet. It is still science, still valuable, just not aliens. The lesson is that anomalies are opportunities. They make us clarify models, consider new mechanisms, and challenge assumptions. Even if they do not revolutionize physics, they contribute to its development. The acceleration of Oumuamua, even if it's just a gas outburst, made Comet scientists think deeper about sublimation at low temperatures, exotic ices, and surface properties. This is progress. The 3-component atlas is another possibility. Its water production challenges our understanding of the activation distances of volatile substances. Its nickel anomaly forces us to reconsider the chemistry of metals in comets, which we largely ignored because our comets do not exhibit strong metallic emissions. The prevalence of carbon dioxide raises questions about conditions in protoplanetary disks in other systems. When enough anomalies accumulate, patterns may emerge. Perhaps strange radio circles and rapid radio bursts are connected, both relating to energy emissions from galactic centers. Perhaps interstellar objects like Oumuamua and the 3-component atlas represent different populations with various formation mechanisms. Perhaps the fleeting zoo of astronomical phenomena tells us something fundamental about the energy of our universe. Or perhaps it is just a series of oddities that coincided in time because we finally have the technology to detect them. In any case, both options are useful for understanding. The key point is to maintain skepticism and wonder at the same time. One can rejoice in the anomaly without claiming it rewrites physics. One can explore strange possibilities without getting attached to them. One can change their opinion when new facts emerge. Good scientific communication is crucial here. When reporting on events related to Comet Tri-I Atlas, responsible journalists and scientists should say, "This comet is behaving unusually. We are exploring several possible explanations. This is what we know so far, but not. The foreign comet violates the laws of physics, and not. Scientists are baffled by the impossible object, but nuances do not attract attention. Cautious wording does not go viral, and so the hype machine continues to operate, turning every anomaly into a potential revolution, creating disappointment when a mundane explanation appears. The solution is not to stop highlighting anomalies. The solution is to be honest about uncertainty. to present multiple hypotheses and update them as new data emerges. The public should be treated as adults capable of handling ambiguity, as they truly can. Most people understand that science is a process, that answers evolve, and that not knowing is a perfectly acceptable answer. Comet Tri-I Atlas is one of the anomalies among many. It is important, it fascinates. But for now, it is not proof of anything. It is just a data point, a mystery, an opportunity for exploration. Regardless of whether it turns out to be a strange natural comet or something we have never seen before, the process of studying it, testing hypotheses, and ruling out explanations is valuable. This process is science, and science, when done honestly, is one of humanity's greatest achievements, especially when it confronts things it does not yet understand. Part 15. Final Reflections. Alive, but natural. So here we are, thousands of words about the mystery of Tri-I, an interstellar comet pouring water into space where water shouldn't flow, shimmering green due to nickel and cyanide, turning on and off as if done intentionally. A carrier of chemistry from another star system, possibly from a different era in the history of the galaxy. Is it alive? In a poetic sense, perhaps it is dynamic, changeable, reacting to the environment, active when it should be at rest, behaving as if it has a purpose, though we know it is dictated by physics and chemistry, not intention, but literally, almost certainly not. There is no evidence of biology here. No metabolic processes, no reproduction, no storage and transmission of information, no distinguishing features of life as we understand it. 3 and Atlas is a stone covered in ice, heated by sunlight, which releases gas and dust according to physical laws. However, these physical laws give rise to something we have never observed before. Sublimation of water at unprecedented distances, nickel without iron, dominance of carbon dioxide, behavior indicating a complex internal structure or exotic compositions of ice. Each new observation adds another element to the mystery. So what is this? The most likely explanation is that the 3 Atlas comets are natural comets formed under conditions vastly different from those observed in our solar system. Perhaps it formed farther from its star, in a colder region where carbon dioxide ice is much more common than water ice. Perhaps her parent star had an unusual composition, leading to strange metal proportions, or cosmic influences over billions of years in interstellar space altered her surface chemistry. The hypothesis of a metallic organism is intriguing. If nickel was involved in volatile compounds like nickel carbonyl, it could explain the disjointed emissions. This would require specific chemical conditions during formation, but nothing impossible. It's just unusual. The origin from a thick disk looks convincing. If the 3 Atlas stars are indeed 7 billion years old, carrying isotopic signatures from an earlier era of galactic chemistry, it would explain some oddities. Ancient ice, ancient chemistry, ancient minerals, all preserved in the deep cold of interstellar space and now emerging as the comet warms. Could this be artificial? Could it be a probe? A derelict spacecraft? Some technological artifact? The evidence does not confirm this. Nothing in the 3 AIs of Atlas requires a technological explanation. Everything we see can be explained, or at least potentially explained, by natural processes. Attracting attention to aliens is not necessary, but let's consider this thought for a moment. If you wanted to design something that could survive interstellar travel and still be discovered billions of years later, how would you do it? You would likely use an object resembling a comet as a shell, protecting your cargo with ice and stones. You could include unusual chemical signatures, markers that would stand out in spectral analysis. Would you allow natural sublimation to reveal these markers as the object approaches the star? This is pure speculation. There is no evidence for this, but it is worth noting that if we ever encounter an artificial interstellar object, it might not look artificial at first glance. It may look like a comet. A strange comet, of course, but explainable as natural until you delve into the details. 3 Atlas is not it, probably almost exactly. But the fact that we are even asking this question says something. This suggests that this comet is strange enough to ignite our imagination, prompting us to ponder and consider possibilities we usually dismiss. Perhaps therein lies its true value. It's not about whether the 3 AIs of Atlas are natural or artificial, nor whether their chemistry is merely unusual or truly revolutionary. It's about how they make us think. urging us to question our assumptions. This reminds us that the universe is larger and stranger than our small corner, that nature has had billions of years and trillions of star systems to explore chemical space, and that we have only begun to study the possible. Every interstellar visitor represents a challenge. He challenges our models, our theories, our understanding of what is normal, and it is through these challenges that we develop. Oumuamua challenged our understanding of cometary activity. The second object, Borisov, questioned our assumptions about the amount of carbon monoxide. The third object, Atlas, calls everything into question. The budgets of flying substances, metallurgy, activity distances, the diversity of compositions, all of it is in doubt. The next steps are clear. Watch Atlas as it approaches perihelion. Measure everything: spectra, light curves, gas emission indicators, the ratio of dust to gas. Look for new lines of radiation. Watch for the appearance of iron or the persistence of nickel anomaly. Compare observations with models, refine these models, generate predictions, test them, and prepare for the next interstellar guest, because it will surely appear, and not alone. The galaxy is full of such wanderers, and our detection technologies improve every year. Each new object will be a new puzzle, a new set of clues, a new window into how planetary systems form and evolve in diverse stellar environments. Perhaps one day we will intercept one of them. We will land on it, drill into it, and bring back samples. We will analyze its isotopes in earthly laboratories, study its minerals under electron microscopes, search for prebiotic molecules in its organic composition, and learn things we cannot even imagine now. Until then, we observe, measure, and marvel, because that's how people act. We look at the universe and ask questions. Why is this comet active so far from the sun? Where did it come from? What can it tell us? The questions themselves are valuable even before we get answers, because it is the questions that initiate research. The Atlas came from somewhere out there, from distant light years and billions of years, carrying a message written in water, nickel, and cyanide. We did not ask for this message. We do not yet know what it says, but we listen, observe, and learn. And in this act of learning, in this stubborn persistence to understand, we find what may be closest to life in this whole story. Not a comet, but we, curious, amazed, striving to touch something that has come from incredibly far away, trying to read a letter from another world. The universe continues to send these letters, cosmic postcards, messages in bottles, visitors from the dark, and each time one arrives, we are reminded that we live in a vast, ancient, incomprehensibly rich cosmos. In the cosmos which forever surpasses our understanding, always astonishes us, and always presents new mysteries. Atlas is one mystery, one comet in the infinite sky, but it is now our mystery. Whether it is just a piece of ancient ice or something more, whether the mysteries reveal themselves easily or resist for decades, we will continue to search. We will continue to ask questions. We will listen closely to what the universe is trying to tell us. Because this is the essence of humanity. To see something strange in the night sky and refuse to look away, to demand answers even when the universe is silent, to find wonder in the stream of water molecules ejected at 40 kilograms per second, in the green light of nickel that should not be here, in the trajectory pointing to stars we will never reach. We are small. The universe is immense. But between us and this abyss, between our telescopes and those distant comets, between our questions and any answers we can find, there is a conversation. A slow conversation spanning centuries and light years, written in photons and spectral lines, in orbital mechanics. 3 and Atlas spoke, we heard him, and continue to listen to what he might say next.